So picking up from where we left off with our new and improved cosmic potential energy equation, suppose a missile is launched straight up from the surface of the Earth. And just to make the math easier, let's suppose it uses all of its fuel, boom, in an initial burst so that there's no continuous acceleration, changing kinetic energy in it. And so as it rises, the only force it experiences is gravity. In fact, let's go one further. Let's ignore air resistance. So this is a really realistic question. Shut up. We're just trying to keep the physics nice. As it rises, what happens to its kinetic energy? And what happens to its orbital potential energy? Well, as it rises, what would happen to its kinetic energy? Would it be speeding up, slowing down, or staying the same? So we're firing all the fuel at one burst, boom, and then shutting off the engine. What would happen to its speed? Decreasing. Be slowly slowing down. In fact, it would eventually, basically this is like on a cosmic level, throwing a baseball into the air. All the kinetic energy is right when it leaves your hand. And what happens to its kinetic energy as it goes higher and higher and higher and higher and higher? Decreases. Eventually there would become a magic point when it comes to a stop and starts to fall back down. So the kinetic energy decreases. Oh, well then, based on the law of conservation of energy, what happens to its orbital potential energy? Increases. Until you reach maximum orbital potential energy, and then you come crashing back down. Correct answer here is C. All right, let's do a thought experiment. And again, Hakeem, let's magically ignore air resistance. Supposing I wanted to fire my rocket thruster, boom, full power, and shut it off, but not fall back down to Earth. We call that escape velocity. What if I wanted to fire my rocket so that I could get away from the Earth and keep going? Yes, slowing down still, but never falling back. So escape velocity asks, how much work is necessary to bring the potential energy to zero? How much work is necessary to bring the potential energy to zero? We can solve for an escape velocity by using conservation of energy. We can say, hey, is there a change in height? Is there a change in speed? Yes and yes. This is a job for so far, so good. Our initial kinetic energy, we're going to assume now, Alex, this is a split second after we've left the ground, so we're not at rest. We're saying, you know what? This is what you're firing your rocket thrust at. And our initial potential energy, can I use MGH? Cliff's shaking his head. No, we got to go cosmic. So it's going to be negative big G, big M, little m, all over, I think, radius of the Earth equals. We want to reach the edge of the universe. This is our theory. When I get to the edge of the universe, in our theory, how much potential energy will I have relative to zero at infinity? How much potential energy will I have out there if I just get there to the edge of the universe? It's not meant to be a trick question, but it's a theoretical question. How much energy, if I get to the edge of the universe, how much potential energy will I have? Zero. So the potential energy final is going to be zero. And, Harjot, if I want to do this just right, what I want you to imagine is I fire my rockets on the Earth, and I start to shoot away from the Earth, but the Earth is always tugging back at me. I'm slowing down, I'm slowing down, I'm slowing down, I'm slowing down. But I am going to get to the edge of the universe, but I'm going to plan this so perfectly that just when I get to the edge of the universe, I'm going to coast to a stop. That's how perfect we're going to plan this. Can you imagine that? Which means, what's my final kinetic energy going to be? I want to say this. This is how I can calculate what the escape velocity necessary to leave a planet is. This is ignoring air resistance. Factoring in air resistance would be much more complicated. You need calculus. But here's our start. What do I have on the right-hand side? 2 zeros. And I can't help noticing that this here is negative. I'm going to plus it over. I'm going to rewrite this as a half m v initial squared equals big G, big M, little m, all over our initial, or our Earth in this case. Our planet, whatever escape velocity from whatever planet you want to calculate. Oh, hey, I noticed something. Do you see it? Turns out, doesn't matter whether you're trying to launch a little satellite or the space shuttle, they will have the same escape velocity regardless of their mass. It's just one will take more energy. And I want to get the V by itself. And I'm going to call this now V-esque for escape. I guess I got that 1/2. How would I move that 1/2 over? Sorry? Times by 2, and that gives me a v squared. Get rid of the squared by. You know what escape velocity is from any planet? Looks like it's 2 times big G, big M, over your initial radius of your planet. Square root. It's kind of a nice answer. That's the escape velocity that you need if you want to fire all of your rockets at once, boom, and then shut them off and coast to the edge of the universe. And again, this is all very theoretical because will you ever reach the edge of the universe? Okay, technically no, but coast to, you know what? To be free of the Earth's gravitational pull, you need at least that, you need to leave the Earth at least that speed. Okay. And we can do this. In fact, we did this to get to the moon. We got escape velocity. We reached the point where the moon's gravity was stronger than the Earth, and we were coasting and accelerating towards the moon in that free return trajectory. So, you know what? I'm kind of curious. What is the escape velocity, A, for the Earth, and B, for the moon? So this formula, this equation for escape velocity, not on your formula sheet, but I've showed you it's not too difficult a derivation. It's saying, is there a change in height? Is there a change in speed? That's a job for conservation of energy, not how much work. And, oh, it turns out at the edge of the universe, you want no kinetic and no potential. You want your final to be 0. So, escape velocity for Earth is going to be the square root of, what did I say it was? 2 big G M over R. And escape velocity for Moon, which I would expect to be smaller, is going to be the square root of 2 big G big M over R. I guess this is going to be mass of Moon, R of Moon, and in the first one it's going to be mass of Earth, R of Earth. Both of these are on your formula sheet. I don't have the Moon memorized. 2, 6.67 times 10 to the negative 11. I know the Earth is 5.98 times 10 to the 24th. And I know the Earth is 6.38 times 10 to the 6th. What is the escape velocity from Earth? Oh, square root. I get 11,000, 1,200? 11200? Yes? No? Yeah. which we do. Hey, the Mars rover Curiosity had to achieve escape velocity because, you know how I know? It didn't land on the Earth. Landed on Mars. So we can pull this off. Not so much in the atmosphere, but once we're out of the atmosphere, sure, no problem. Now, out of the atmosphere, the escape velocity required is a little bit less because you're a little bit further from the center of the Earth, but close enough. Hey, what's the escape velocity of the moon? I'm pretty sure this is going to be smaller. Folks, you guys are going to have to give me the data here. I know 6.67 times 10 to the negative 11. Mass of the moon is what? 7.35 times 10 to the... And radius of the moon is... So if we do someday, maybe in your lifetimes, if we do have a moon base, it makes way more sense to launch stuff to the rest of the solar system from the moon. Why? Well, less energy required. Divided by 1.74 times 10 to the 6th. That's what I was wondering. Something was bugging me. 7.3, so it looks good. Square root of that. Is that right? Anybody else get 2370? Yeah. Way smaller. Yeah. Okay. Hey, what would the escape velocity needed to escape the sun be? Well, you could figure that out too. That would be if you somehow wanted to leave our solar system. Although you'd also have to factor in, I think, it's a much more complicated situation because, Mickey, then you'd have to factor in what if you're passing nearby. Jupiter in particular has a pretty strong gravitational field. You might need to take into account that you're going to get deflected. You'd have to take that into account as well. But it starts here. Question? You're good? Okay. Is that okay? Example 5. A mass is released from a height of 6,300 meters above the Earth. How fast will it be going when it hits the ground? And we're going to ignore air resistance. Okay. Do you see the word orbit in this question? Read carefully. No. That suggests to me that I want to use some kind of energy work approach. Is this question saying how much work? Is this question asking how much work? Hakeem is shaking his head correctly. Hakeem, in this question, is there a change in height? Is there a change in speed? This is a job for conservation of energy. However, there is a typo. Can you all look up? Kilometers. 6,300 meters is still close enough to the Earth's surface that I could just go MGH. Okay. So we're dropping, you know what? This is the physics of a meteorite incoming. So this meteor we've spotted, it starts out 6,300 kilometers above the Earth. We spot it out there somewhere. And maybe it's, you know what, an old satellite, a 3,400 kilogram satellite, pretty heavy satellite, so it must be old technology. How fast will it be going when it hits the ground? So again, is this an orbit? Nope. Are they asking how much work? Nope. But there is a change in height, change in speed? Well then, are any of these 0? Well, we're going to assume that it's starting from rest. Doesn't have to be. They could have told me its incoming speed. Now, in our energy unit, when we hit the ground, don't write this down, we would always say that, but I can't say that here because we're using our cosmic version of potential energy. We're relative to zero out at infinity, so I don't think anything else is zero. Let's plug stuff in. Potential energy, can I use MGH? No, we're cosmic. It's going to be m little m over R initial equals a half mv final squared plus negative big G big M little m over R final. Where I think what we're saying here is R final. Oh, forgot the negative on the initial. Thank you. Sloppy. Candy for you. I think R final is the radius of the Earth because that's where we're ending up. I think R initial is 6,300 kilometers plus radius of the Earth. So I'm going to quickly do that. 6,300, that's kilometers. How would I go to meters? Times by 1,000. And the reason it's plus is it says above, so I'm going to add plus 6.38 times 10 to the 6th, and I get 1.268 times 10 to the 7th. Okay. Hey, what are we trying to find here? V final. Yeah, okay. Oh, hey, I noticed something else conveniently. What do you see? The masses cancel, so the mass won't affect how fast it's going. The mass will affect how much damage it does, but a golf ball dropped from that height, if we ignore air resistance, would be the same speed when it hit the ground as a 3,400 kilogram mass. Just, I wouldn't want to be anywhere near the 3,400 kilogram mass when it hits the ground. The golf ball, if it hit the ground 50 meters from me, I'd probably be okay. I hope. Although we could calculate its kinetic energy and actually get a good feel of how much punch it was packing. You said we want to get V final by itself. You know what? I'm going to plus the second potential energy over. I'm going to rewrite this as big G, big M over R final, take away big G, big M over R initial. That equals a half V final squared. I could probably do more algebra, times by 2 and square root, but you know what? I've already typed this in a few times. This is pretty ugly. I'm just going to start crunching numbers, get an answer, and then I'll times by 2 square root. So this is going to be 6.67 times 10 to the negative 11. Which mass? We're around the Earth. And R final was the radius of the Earth, which was 6.38 times 10 to the 6th. Take away, same thing, all over R initial, which was 1.268 times 10 to the 7th. That equals a half V final squared. Have I got more room? Barely, but yes. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 6.38 times 10 to the 6th. $6.2518 times 10 to 1, 2, 3, 4, 5, 6, 7. 6.2518 times 10 to the 7th plus, did I write that down right? 62518, yep. Same number, but negative. I'll put the negative in on my own. 1.268 times 10 to the 7th. So instead of plus, Mr. Dueck, I should have written a minus here. Take away 314,156, 309. Is that right? You good with me, Curtis? I think, yeah. Times 10, 1, 2, 3, 4, 5, 6, 7. 3.1456 times 10 to the 7th. 3.1456. That equals a half V final squared. So now I'm going to go 6. Oh, heck, since I have the number on my screen. 25181.82 minus that number. I missed a digit. Rats. Okay, let's backspace. Let's backspace. Now I'm going to have to use this. 6.2518 times 10 to the 7th minus answer button. Do you get that when you subtract? People nodding. So 3.106 times 10 to the 1, 2, 3, 4, 5, 6, 7. 3.106 times 10 to the 7th. That equals a half V final squared. So I guess V final is going to be 2 times that square root. Am I wrong? No. Times 2, square root. We're going to be hitting the ground at 7,880 meters per second. In terms of its kinetic energy, squared times, what was the mass? 3,500? Times that, was the mass 3,500? Yeah. So if I go a half mv squared, it's hitting the ground with a fair bit of energy. It's going to do some damage. Now, in reality, of course, it's going to slow down in the air. In fact, it may burn up in the atmosphere depending on how fast it's coming in. The air resistance, the air friction might be such that it could burn up. Or, as you saw almost exactly a year ago today, it may explode in the atmosphere into smaller pieces as a meteor might do. Right? We're almost on the 1-year anniversary of that big meteor that exploded over Russia last year, right? You guys saw what they did with the medals in the Olympics? The medals that they were giving out on the anniversary have pieces of the meteor in them. Right, do you guys know that? Kind of cool. Okay. So that's the third kind of question. The third kind of question is this. Dropping something, but instead of just physics 11 potential energy, dropping something on a cosmic scale. Hey, let's start from a few thousand kilometers up or even further and say, okay, how fast you'll be going when you, in this case, when we hit the ground, or I could have said, for example, when we reach a new radius of, and I could have given you a different R final. Is that a question I saw back there? Or are you guys good? Yeah, okay. Did I show you, and did I finish the Death Star video with you guys last class? I did? Okay, I couldn't remember because there was one class that I couldn't quite finish it in. But you guys, I did? I don't think we finished it. Did we? Okay, first of all, I already assigned 1, 2, 3, 4. Okay, I'm going to add 5. So now 7, I assigned last time, but you should be able to handle number 7. Number 8 is fair game. Number 9 is fair game. 10 is fair game. We need to practice this. 11 is good. 12 and 13. So I think I assigned, did I assign everything? Did I skip? No, I skipped 6, right? Skipped 6? Okay. pause, and then we'll finish off the death